Bismillahirrahmanirrahim. Assalamu alaikum. So let's move on. Today we are going to discuss about non-rigid transformations applied to parent functions. When I say non-rigid transformation, I mean those transformations where the original shape of the function, parent function, changes. There are basically two kind of non-rigid transformation. One are so you can basically say that there are four. Number one is vertical stretch. Vertical stretch. When do we observe vertical stretch? For example, this is our parent function. Then a new function that is obtained by multiplying some constant c to f of x represent vertical stretch if c is greater than 1. If your c is greater than 1, then this new function will be representing to a vertical stretch. For example, you have a function f of x equal to absolute of x, and you define now a new function g of x, which is, let's say, 5 times absolute of x. Now this 5 is greater than 1. So this is basically vertical stretch of absolute of x, this parent function. Similarly, if you have another function, let's say f of x to be x square, and you define another function g of x, which is 9 times x square. So this new function is vertical stretched version of this function. Similarly, you can define a function f of x, which is, let's say, reciprocal function, then a new function g of x, which is let's say 10 times 1 by x, or 10 over x. So this is the vertical stretch version of this parent function. What do we mean by vertical stretch? So what does vertical stretch do to the graph of function? So it basically takes the graph away from x-axis. So like if you have a graph of parent graph of this, let's say absolute of x, which looks like this. So when you stretch this vertically, it will move towards the y-axis and away from x-axis. This way you observe the vertical stretch. For example, we can talk about this function f of x equal to absolute of x. This is the original function, and this is the stretched version of this function, 3 times absolute of x. So you can now plot this. First, let's plot this. At 1 it is 1, at 2 it is 2. Okay, so it's 2 here. Let's say at 3 it's 3. Similarly, so that's the parent function. Now we want to plot this function, this one, f of x equal to 3 times absolute of x. So when I will insert 1, it will give me 3 here. When I'll insert 2, it will give me 6 somewhere up, and at minus 1 it will also give me 3. So it will be this way. So it is stretched vertically. Similarly, we can see the vertical stretch to some other functions. For those, I will take you to Desmos. Say y equal to x. This is a parent function, and now we multiply this x by, let's say, 10. So you can see that the graph is vertically stretched, or it has moved towards the y-axis and away from x-axis. Similarly, you can talk about x square. This is the graph of y equal to x square. Then we can multiply some constant, let's say 5 to x square, and then we can observe. So this blue one is the stretched version of this x square. So we have stretched it, and similarly you can even talk about square root of x or 1 by x. This is the parent function, and when you multiply some, let's say 10, then it will be 10 over x. So you can see that what is happening basically. So this is the vertical stretch for reciprocal function. Similarly, you can take square root of x, y equal to square root of x, square root of x, and then you can just multiply this with some constant, let's say 9. So what happens is your graph moves towards y-axis and away from x-axis. Similarly, we have got something else, that is vertical shrink. Let's talk about that. So let's talk about now vertical shrink. Suppose we have a function which is f of x equal to y equal to f of x. Then if you define a new function which is g of x equal to c times f of x, but now your c has to be between 0 and 1. If your c is between 0 and 1, then it will represent to vertical shrink. And vertical shrink means your graph will be, kind of will be moved away from your y-axis, and it will be, something closer towards x-axis. Maybe you can say that. Examples include, let's say f of x is equal to maybe x cube, and I'm going to define another function, let's say g of x equal to so I have to multiply some constant which is between 0 and 1, let's say 1 by 3 x cube. Now this c is greater than 0 and less than 1. So in that case, I will get the shrink version of this, x cube. So this x cube graph will be shrinked. And similarly, now if I define f of x equal to maybe another function, let's say 1 over x, then its shrink version will be g of x equal to, let's say, 1 over 5 times x. Similarly, we can define maybe f of x equal to greatest integer function x, and then we can shrink it. So we have g of x equal to, let's say, 1 over 2 times this greatest integer function. We can plot these functions on Desmos and get the idea what is going on. Let's first sketch x cube. This is the graph of x cube, which is parent function. And we had another function g of x, which was 1 over 3 times of x cube. So this has moved away from your y-axis, and that's the shrinkage version of this x cube. Similarly, we had 1 over x, and then we multiplied it by 1 over 5, 1 over 5 times this x. So this red version is shrink of 1 over x. Similarly, we had defined the greatest integer function, which is y equal to floor of x, and now we had multiplied it with some constant. And what was the constant? It was 1 by 2. So y equal to 1 by 2 times the floor of x. So this green is basically shrinkage version of this blue absolute or greatest integer function. Similarly, we have got horizontal stretch and horizontal shrink. I'll just put the statement how it works, then I'll leave all up to you to work out. So let's talk now about the horizontal shrink or horizontal stretch. So consider you have a function y equal to f of x, and you define a new function with the help of this y equal to f of x, which is g of x equal to f of c times x. Now you multiply your c with x. Previously you were multiplying c with this. So this will be horizontal stretch if your c is basically between 0 and 1. For example, you have a function f of x equal to x cube, and then you define a new function g of x with the help of this function by replacing x with cx. And let's say my c is 1 by 8 x cube, sorry x, so 1 by 8 x cube, so this will be 1 over 8 power 3 times x cube. Now this will show me this new function g of x is basically horizontal straight version of this function. Horizontal straight means it will be, the graph will be moved towards x-axis and away from y-axis. Similarly, let's say you have a function, let's say f of x equal to absolute of x, and now you kind of define a new function g of x, which is you multiply some constant with this x, let's say 1 over 4x. So now this function will be, kind of horizontal stretch of this. Similarly, you can define this for other functions as well, and for this even 1 over 4 can be taken common, and this is basically equivalent to vertical stretch. So horizontal or vertical shrink. So horizontal stretch can be seen as vertical shrink. And then we have horizontal shrink. So let's say we have a function which is y equal to f of x, and now you replace this x with c of x by defining a new function g of x, which is your x is replaced by some c, and your c is greater than 1. So for example, you have a function f of x equal to let's say greatest integer function, and now you define a new function g of x equal to multiply here some constant, let's say 2x. Similarly, you have a function f of x which is, let's say, at square root x, and you define a new function g of x by multiplying some number here with x, let's say 5x. So these are horizontal shrinkage version of these. So you can plot them on Desmos and get the idea. So what will happen basically in the horizontal shrink, your graph will be moved away from x-axis, and it will be towards y, somehow towards y I can say, but roughly speaking it will be away from kind of x. We can plot this. So this is the graph of square root, and now you multiply it with 5. So that is the horizontal basically shrink. So it's kind of the graph will be away from this x-axis, and in fact you can plot its horizontal stretch, horizontal 1 by 3 horizontal stretch version. So you can see that horizontal stretch means graph will be towards x-axis, and horizontal shrink means away from x-axis. In fact, you can demonstrate it this way. Let me run this k. So let's say our k is moving from 0.1 to let's say 2, and with the gap of 0.1. So you will see that when our k is between 0 and 1, you will have between 0 and 1 what we have horizontal stretch, and k greater than 1 horizontal shrink. So it's, you can see that's when k is less than 1 you have horizontal stretch, otherwise horizontal shrink.